few varieties developed to record the sound.
I should, right?
Yeah.
Okay.
So I think probably we can start.
Yeah, sure.
Okay, good morning. Let's go ahead and get started. Welcome to today's special seminar. It's our great pleasure to invite Professor Stephen Shi from National Central University. Professor Shi is a distinguished professor at mechanical engineering there, and he got his PhD from University of Washington in 1990, and then 1.5 year postdoc at Princeton University. So after that, he joined NCU as associate professor and then promoted to full professor in 1997. So Professor Shi is very famous in the community of combustion, and he was the director of the Center for Energy Research at the College of Engineering at NCU from 2003 to 2014. And his research mainly on combustion, but on different aspects. And currently, he worked on high pressure, high temperature, lean premixed combustion relevant to the gas turbine applications. And also, he's working on pressurized ammonia for like fuel cell applications and try to develop some kind of hybrid micro gas turbine applications. So as I just mentioned, he's very famous in the community. He's the former session chair, Taiwan session chair of the Combustion Institute. And he was elected to the fellow of Combustion Institute in 2019. That's like, the early classes are very prestigious. It's very difficult to get in as a fellow. So he served as an editorial member for Proceedings of Combustion and Proceedings of Combustion Institute, and as an associate editor since from 2008 to 2013. And then currently, Professor Shi is the editorial board for Combustion Flame. So this is the #1 journal in combustion community. And so he served 6 years there. So he was the recipient of the Outstanding Research Award from the National Science and Technology Council of Taiwan. So last but not least, I want to mention that Professor Shi likes swimming, cycling, and running. So he completed the full triathlon, and very impressive. Okay, with that.
Okay, thank you very much, Professor Fan, for kindness introduction. I have to wear this for recording purpose. Yeah, it's online. I don't know how many people online, but thank you, Professor John, and to attend. Okay, this I know the school starts 21st. So right now I'm great. There are more than 5 people to come. Yeah, usually I expect 5. Yeah. Anyway, my name you can call me Stephen. And although this is shy, I pronounce Shi. Sorry, I picked the name and the force people to pronounce Shi. Yeah. Anyway, in this talk, I would like to speak on spark ignition transition. I will explain this later. And this is premixed turbulent combustion. Like Professor Fan said, related to the gasoline engine and gas turbine. So let me introduce you if you don't know where Taiwan is. Yeah, very close to China. Yeah, and Japan, Korea, Malaysia, Thailand, and we have about 23 million people, and the most on the west coast here. Yeah, and marine tropic climate. So it's a warm place. Right now it's humid and hot right now. Yeah, but the winter in December average temperature is 20 degrees Celsius. Okay, so here is where I am. Taoyuan is 1 hour south of Taiwan, but if you take the high-speed railway, it's like 20 minutes. So when you arrive Taiwan, it will arrive Taoyuan International Airport, and the NCU is about 30 minutes drive by car. And this is my university. I know some of you can recognize this Central University. Yeah. Anyway, so I know is you will have a question because electrical vehicle is growing tremendously. Okay, a newer car produced in average is between 80 million to 100 million. Okay, and in 2020, it's only 4%. Okay, it's something like a 3 million car, and increasing 5%, not to 9%, 5% to 14%, and the 5% expected in at least 2023. So they will reach like a 15%. I mean more than maybe 20%. Okay, so 80% is still run by the internal combustion engine. Yeah, and recently renewable energy are developing. So if you use we so-called the hydrogen economy, and there are gray hydrogen and blue hydrogen and green hydrogen. And I know probably you know this already, but gray hydrogen means like you use the methane or some kind of the fossil fuel and to reform to the hydrogen, and it's produce CO2. Okay, so that's the gray. Okay, but if you use the carbon storage, sequestration, utilization, then that's called a blue energy, blue hydrogen. Okay, but if you use the renewable energy, okay, something like a solar energy or wind power energy, and you in the life cycle, no CO2, net zero CO2 can be achieved, and that's called a green hydrogen. Okay, so anyway, if renewable energy can be developed, and electricity can use to split water or even purify the CO2 and produce the hydrogen by renewable, I think I'm out of this one. Yeah. So maybe Professor Fang can the pointer, if you have a pointer. Yeah. Otherwise, I will come to here and just. Sorry about that. Okay, I need a pointer. So let's see how I can get a pointer, like a laser pointer. Okay, use this probably better. Okay, so the idea is to use the renewable energy to produce hydrogen, and capture carbon and produce so-called the e-fuel. Okay, I will introduce this a little bit, and hopefully it can use in the internal combustion engine. Okay, yeah. So to close to audience, thank you very much. So e-fuel is electricity fuel, and there are also a recycled metal fuel. Recently, by the Besson paper, a review paper for the clean and compact zero carbon power. So you can see the boron and those metal. This is, I think, is 5. Helium is 2. This boron is 4 in the chemical element. Anyway, this is a liquefied hydrogen and the compressed like a 700 atmosphere for the hydrogen gas. So you can see the specific power density. This is extremely high. If the recycled metal in nanoparticle can be used in internal engine, then internal engine since 1860 something, then still can be used. Okay, and this is not produce any hydrocarbon. Okay, and recently they're developing ammonia in gasoline in the gas turbine. Yeah, so that's also little carbon, and the e-fuel, metal fuel, if they can use in the internal engine, people, I think internal combustion engine, they think they can use. Okay, yeah. But we are not 100% sure, okay, and how it affect the performance. But somehow the lifetime cycle assessment tell us the average of electrical car is like something like 8 years. Okay, so the battery will go bad, and so recycling battery is very important. Yeah. So anyway. The answer for the spark ignition engine will replace by EV. Probably they will reach some point, yeah. And it's starting the electrical vehicle, the lithium-ion battery, need to disposal, need to recycle, and this problem haven't solved yet. Okay, so soon. Within like a couple years, we will see massive disposal battery. They may be used to store the solar energy or wind power. I mean, because their performance is less than 50%, and nobody wants to drive the EV car, EV for 50% performance. Okay, most people buy the Tesla for its high performance, not. Yeah, so they will have a problem. So from this lifetime cycle assessment, I think from the synthesized fuel by electricity to synthesize gasoline or diesel and use in the internal combustion engine will be continue for decades. Okay. Of course, we want to reduce it. That's for sure. And the electrical car is growing. It's growing, continue to growing. But to some point, due to this battery, you need to recycle or this kind of thing, and it will be probably 50-50, I guess. Okay, so. I don't bother you with this because I just say, and United Nations like 2050 net zero, and so we need action, yeah. And electrical vehicle, of course, is one of the energy transportation, but for power plant, yeah, and that's another. So we it's like Indian. Proverb always say the earth is not what we inherit from our ancient. It is what we borrow from our children. So we need to do something, of course. And the IC engine and the gasoline for transportation and power generation using the low carbon or little carbon renewable fuel. For instance, electro fuel and the recyclable metal fuel. This is, I think, this is important in the future. Okay, but I'm not going to talk much about the. I will use just the few that I can get. So you can have this e-fuel information in the current review paper. That I just published online. and spark ignition transition. I will explain what's that mean. Spark ignition, I think everyone knows. I mean, because spark ignition has been used for more than 160 years, okay, since 1840, and still using today, okay. And premixed turbulent combustion is like your fuel and the oxidizer mixed together, and you ignite and produce power and do the work. So my talk will probably 90% based on this paper. Okay, so if you don't understand my talk, you can go to the this number here, volume 98, and just appeared recently. Yeah. So I will introduce you to transition. This MAE is a minimal ignition energy. It has specific definition. Yeah, I will introduce later. And the non-monotonic MAE transition. So I draw a cartoon to just let you know. In turbulent combustion, and because turbulent itself is so complicated, so we want to create the simplest turbulence using like a fan or with perforative, some kind in a pump or in a burner, closed burner, and so fan stir burner, okay, and they are two parameters from turbulence. One is the turbulent intensity, turbulent root mean square, turbulent fluctuation velocity, to simplify, because isotropic turbulence is like no direction, preferred direction. So mean velocity are negligible, and root mean square turbulent fluctuation velocity in all three directions have equal magnitude. That's the best. Okay. So the best we can do is try to do something like that. And also there is a length scale problem. Okay, so we need to have a PIV or LDV, some sort of a tool to measure that. Okay. And the largest AD is like integral length scale of turbulence, okay, which is of course, the largest scale is your device, okay, and the fan generates a lot of AD, okay, from large to small. The smallest AD is Kolmogorov scale, yeah. So if you take in the class of turbulence, you will know what I'm talking about, okay. Large scale and small scale, there is a cascade, Kolmogorov cascade, first principle and second principle. So the thing that I want to introduce is minimal ignition energy is kind of this is normalized by its laminar. Okay, so the first one is the so-called monotonic MAE transition. When you increase in turbulence, then normalized by this laminar fan speed. Okay, normally. This is the common notion. Turbulence random, ignition more difficult. So it's increased. But to some critical value, the increase of the ignition energy is exponentially. Okay, so this is I call transition from gradually increase to transition. And why is that? I will explain in this talk, okay? And if the electrode, I mean the spark gap from the electrode and the fuel, I mean there is diffusion, there is differential diffusion instability. That's a thermal diffusional instability that I will talk about in detail later. Under some restricted condition, okay? The modest or the weak or modest turbulence actually facilitate the ignition. So you don't need ignition. You have a decrease slope. Okay, your ignition energy is smaller than the ignition energy in cohesion. But this is not easy to happen. Okay, you have to have some certain condition, like a Lewis number. Lewis number is a diffusivity ratio. Okay, between thermal and the mass. Mass diffusivity is the deficit diffusivity. Okay, if that is much greater than 1, okay, and because the spark has a curvature, positive curvature, so positive stretch will weaken reaction rate, so that the turbulence actually weaken, facilitate, weaken reaction, so facilitate ignition. So easy to ignite in the turbulence. Okay, and this I call it TFI. I also will explain what is it and how it happened and why it's happened. Okay, that's the two main topic. Okay, two extremely phenomena. And if turbulence is strong enough, it's become exponential growth again. And this part of physics are the same, so I will not put time on here because I only have 50 minutes, and I hope you can ask question with the last 10 minutes. Yeah. Okay, so let's think this. First, the ignition is statistical. Okay, even you use the same ignition, spark ignition energy, sometimes you ignite, sometimes there's no ignition. Okay, even you use that. So there is an overlapping regime. Okay, this is the Banner and Joe Schaefer at the Caltech. Well, some other people already know this a long time, but he has a thesis detail this. Okay, so it's statistical in nature. Okay, and ignition probability, 1%, 10%, 50%, or 80%. There are many. Sometimes they are not well defined. 1% or 10%, in the powder, in the gunpowder factory, they are more important than 50% or 80%. Because if you have a servo, you have a computer, all the servo is running, and they generate a very small metal particle. And if you accumulate, if the ventilation is not so good, and you have a spark and blow everything, that's really disaster. So they measure the 1%. Okay, 1% is difficult to measure. You need to do thousands of experiments to get that 1% right. Okay, so the one that I'm talking about is 50%. It's easiest to measure. It's not so easy. You need to do repeated run and to get this because it's statistical. So 50% is statistical in nature. You get a 50%. So the minimum ignition energy is defined as the ignition energy at the 50% ignitability. Okay, and this is the most common definition in our use in our combustion community. Okay. So how accurate we can measure it, and how to define MAE, I already did, and which factor influence the minimum ignition energy. Okay, so even though this is very simple, you use a pair of electrode in the laboratory, and you connect to your power source, and you give a spark, but the energy itself can be influenced by the electro characteristics, like a material. Okay, you use the stainless or tungsten, that will be very different because conductivity will quite different. And the geometry, you use the flat end or the sharp end or the wrong end, that will change your energy. Yeah, and the size and the gap also. Thickness of the electrode and then large conductivity heat loss, and the gap, small gap, very large heat loss, and longer gap. Okay, and those nice things. So discharge character, flow character, like a turbulence, temperature, pressure, mixture characteristic. So in order to let the other people repeat your experiment, you need to specify those conditions in the paper. Yeah, but not every paper did that. Okay, so it's hard to repeat, compare, and this is the point that I make in the PEC review paper, and so I try to give everything that people allow other people to verify and to repeat experiments. Otherwise, the worst kind research is misleading research. Yeah, if you have a misleading research, that's worst. Okay, this is the car automobile ignition coil. If you ignite like that, you measure the voltage and the current, you integrate, you get something like a 30 to 61. It's vary. Yeah. Even if you spark every time, it's vary. Yeah. And you have a peak here, and there are lots of oscillation. Yeah. And this is the millisecond. Yeah, millisecond. So they can last quite long. So this is large uncertainty if you use the coil. Okay. Of course, if the purpose to ignite the mixture without knowing how much, you don't care the ignition energy precisely. That's okay. That's perfect. You just ignite, it just burn. And the nice thing is, like a spherical flame in a closed chamber, you ignite, and when the flame kernel reach its critical radius, it's forget the ignition source. No matter how large it can. Of course, I shouldn't say no matter how large. If you use the atomic bomb, everything burn. That's totally different story. Okay, that's detonation. Okay, but for the something like 10 joule, I mean below 10 joule. Okay, then gasoline you only need like not the 61 joule. You sometimes depending on the gap size, if you like a 2 millimeter, you can ignite within like less than 5 millijoule. You can ignite. Okay. Anyway, so this is not too precise, and every time it change. Yeah. So if you want to do it more correctly, and if you have, of course, you need to have a post generator. They don't. This company, I think they closed. Yeah, but somehow one of my students can. We have a several of these, and some parts are broken, so we just buy the parts and to replace and make it work again, and this can produce the near square wave. Okay, so and we can control the post duration time. So in other words, the purpose here is that we use the loading resistor here to control, and this is in series or parallel, and we can control the ignition energy from like 0.2 millijoule to something like 500 millijoule or even one joule. Okay. So anyway, the purpose here is like a square wave form of voltage and current will give you more precise. Okay, energy measurement with small uncertainty. Okay, so this chamber is what I use mostly. I mean, in this paper, we will talk based on this. Of course, others also review. Okay, so this is pretty big. Okay, so it's like 1.1 diameter, inside diameter, and more than 2 meters in length. And inside there is an inner chamber. Okay, there is a horizontal and this cruciform shape. If you look three-dimensional, it's like a cruciform in all three directions. Okay, so there is a fan and there is a perforated pail, okay, driven by 10 horsepower, and so it's a counter-rotating. Okay, we found it must be counter-rotating in order to create a near isotropic turbulence. So please, if you are interested in how we generate the turbulence, then please read the review paper, and there is a reference, and you can find. Okay, so this is the primary perforated plate with the, with the heating wire, and so this is very effective convection heat. Convection heat. We can heat up. This is closed. Okay, that's the cross window, 4 cross window from 4 sides, and this is the nanosecond repetitive pulse. It's a plasma assisted. So anyway, I will come back to this later. And we just use the shielding technique to look. This is a hydrogen. Yeah, hydrogen you cannot see. It's not visible. Yeah, you cannot see from the eyes. Okay, you have to use the infrared camera or shielding to see the hydrogen flame. So hydrogen flame is very dangerous. Of course, corrosion too. And so they are surface heating. Surface heating is like they are 17 kilowatt. We have like a 20 piece. Before experiments, we have to heat up. If we do the isooctane or corrosion is like auto-ignition is like something like a 200 degrees Celsius. So the perforated plate is already over it. Yeah. So it's hard for me to do corrosion, but somehow we have to do like a 100 degrees C. We cannot do like a 200. Yeah. So if they just auto-ignition, this is detonation. Yeah. So this cross window will break. But somehow that's a weak point. The cross window is like 5 centimeter, and the sum is 10 centimeter. Yeah. We have a weak point design. So and this chamber, this outer chamber is for safety. No matter what's happened inside, outside, people don't get hurt. Okay, so this is very stout. At least we can pressurize this outer pressure safety chamber to 12 atmosphere. Yeah, maybe more than that, but we have a regulation. More than 10 atmosphere, we have to inspection, and we have to get license. And so I just say, okay, we operate below 10 atmosphere. Okay, so we can create, so the counter-rotating, and we can create, this is like 30 centimeter, from here to here is 40 centimeter, but in the center, from the vertical tube, horizontal tube, and this is a large horizontal tube, is about 30 centimeter, okay? So we can near isotropic turbulence a large volume here, okay? So we ignite in the center, okay, of a uniform region. And I'm going to tell you, we have a release valve too, okay? So the first thing to do the experiment is to vacuum both chamber, okay? And we pressurize outer chamber to gradually, okay? And we inject, normally we will have a mixing chamber, additional mixing chamber to mix the fuel that we want, and eject into the inner chamber, okay? With the pressure slightly less than the outer chamber, okay? So it's like take time to do that. Okay, once we done, okay? This is additional secondary heat air, because this surface heat, you need 3 or 4 hours to heat up. If you want to do 150 degrees Celsius, it takes like 4 hours. But but it's not going to uniform. Temperature is not uniform because surface is hot in the center. So there is a temperature gradient. But people use that because their chamber are small. So the temperature gradient won't differ much. But my chamber is large, so there is a large temperature gradient. So I have to figure out, so finally we decide to, before this plate is used to generate the turbulence, okay, like a jet here, and they mix in the center, and they create a near isotropic turbulence. But with the heating, the convection heating is very effective. So the temperature uniformity is very, very good. Okay, we use the thermocouple to measure and publish in some journal. Anyway, since there is no mean velocity, okay, unlike the jet frame has a strong mean velocity and the turbulence, so it's quite complicated to analyze. So I like this spherical frame because there is negligible mean velocity. We only consider the turbulent fluctuation velocity. The largest that can go like 8 meters per second. Okay, so that's a fin frequency and the integral length scale. I don't go this in detail, but somehow increasing the fin frequency, counter-rotating fin frequency through the perforated plate, and please take my word, near isotropic turbulence. Okay, we can see the frame. If the frame in non-uniform turbulence, they will stretch by turbulence, so they will not look spherical. Okay, but if near isotropic, of course, unless your turbulence is really strong, tear apart the premixed frame. So frame and the product and the reactant, they all mix together. We will talk about distributed like frame. Okay, I better watch my time. Yeah. So let's see the video. Yeah. So this is gold case. Okay, the same energy that we use. Okay, and this is the isooctane at 100 degrees C. This is the no-go case. Even you use the sending ignition engine, one go, one no-go. Okay. I better stand here, so saving time. And this is for the turbulent case, okay? And much stronger ignition energy is needed to ignite, okay? And that's U-prime over SL at 5. So that's turbulent go case, no go case. Okay, so there is, in the paper, I introduced two systematic logistic regression methods is recommended, okay? And most people, they measure the MAE, they maybe do 10 times. And if 10 times no ignition, that's fail, no go, okay? If only 1 times they ignite successfully, developing to spherical frame, then this called ignition, successful ignition. So it's about 10%, but because only 10 run, so it's not too good. But this logistic will give you more precise, 50%. But if you want to do the 1%, you need to do thousands, okay? So there is an overlapping regime, okay? Ignition successfully, failure ignition coexist, okay? And this is normally we do 30 to get the 50%, but this is the ignition energy. But I think 18%, the smallest number data point you need using this measure, something like 18, you can within 10% uncertainty. Okay. So anyway, this is the monotonic MAE transition. This is the most important figure to explain. Okay, although this is in a log plot, but somehow this is gradually. You can see the exponent. MAE as a function of U-prime over SL, normalized turbulent intensity. This is 0.7, this is 7. So one order magnitude larger. So this is gradual increase, this is exponential increase. So we call it a MAE transition, okay? So in engine, usually we operate in a highly turbulent flow, in gasoline and in gas turbine too. Yeah, so that's why ignition is so difficult, okay? In engine, sometimes misfire. And we don't want a car, you cannot ignite, and you ignite so many times, and this car you won't buy, right? We want ignite directly, right? And let's go. Yeah. So ignition energy is that's explained. We need a certain gap, okay? Because this gap size will influence the spark. Of course, the spark design usually in current industry is like a 0.6 to like a 1.2 millimeter. Okay, so it's still small. and that's not the best. Yeah, that's not the best. Probably around 2 millimeters is better. They will have a misfire reduced drastically if keep the same thing, just increasing the gap. Yeah, but of course the corrosion, because a larger gap, maybe lifetime is shorter because they need a high voltage. Yeah. Anyway, so I'm not going to talk too much about the application. I focus on the fundamental, make it clear in this code. This is laminar. You ignite in the center of that cool sulfur burner, and that's the laminar. And this is the kernel, like friended. I mean, I'm not sure you know the. We have a laminar frame, we have a friended, we have turbulent friended, we have corrugated friended, and then we have a thin reaction zone, we have a broken reaction zone, we have that's a phase diagram. Yeah, but the phase diagram itself is still, many people apply it. I didn't show it here, but what I want to show you is a distributed light kernel. In the kernel, like this one is pretty much the same. But the turbulence here is much large, so it's break, okay, to the broken reaction zone, similar, okay. In the jet fan, you never see this, okay, you never see this, because this is no mean flow, okay. So this is maybe distributed like, okay, distributed like a bird, filiform, like a firework, yeah. Anyway. So we see the quite different structure. This is still like a spherical frame in the end, and this is the laminar, this is turbulent. But for the distributed, very large turbulent intensity, we see that, okay? And this is 2010, and this is the electrode we use, and this is stainless steel, and this is different equivalence ratio. So they have a different critical radius, critical U-prime over SL for the MAE transition. Okay, and I will show you all the data can be collapsed. Okay, this is Karlovitz number. Okay, so they vary from something like 8 to like a 26 here. And with the minimum at a little bit rich than the stoichiometric. Okay, so here again, here is the high pressure to laminar and modest turbulence, and this is strong turbulence. Okay, in the exponential growth region, and so this may be. Corresponds to why the MAE need so high ignition energy in the post-transition region. Because this island, this broken reaction zone quench, and in order to make it survive and develop, you need much higher ignition energy than the pre-transition. Okay. Pre-transition is just ignition energy gradually increase. But in the post-transition, you need whole lot bigger ignition energy because there are local quench occur and make the flame alive, survive more difficult unless you provide sufficiently large U-prime over SL. Okay, so your MAE is much larger than your. This is just 1.6. This is like almost 200. Okay, and broken iron, this B is quenched. Okay, so this is the high pressure, and it's the same thing distributed here. This is the high U-prime, and that's corresponding to gas turbine. And high thermal efficiency engine. They have a highly tumble flow and using the super lean burn. So their SL is small, their U-prime is large. So this is corresponding to that high thermal efficiency. Like in Japan, they have a ship project and they have a gasoline engine reach 51% thermal efficiency. Currently, it's like normally it's like a 30, 35. Yeah. Anyway, so the other part, like mass in Germany, so they find the same thing. Okay, they find a similar thing. Okay, similar thing for the methane. I don't go in detail. This is the flow chamber. Okay, it's different. So they have a mean flow. And the laser ignition also find laser is decaying, so they have to average to get the U-prime. But they find a similar transition after, I think the first one is the mass found, but he didn't say anything about the MAE transition. I said it in 2007, but at that time I didn't know his work because he is not published in Combustion and Flame. He is published in he knows this kind of journal. This journal is a prevention. Is in the 80s. This is corresponding to the paper review paper of MAE, so you can check that. And the DNS, okay, Chapotti in England, he find similar to the laser ignition. And he also find a broken reaction zone. Yeah. So anyway, if you plot a critical for the pre-transition and post-transition Karlovich number, and as a function of Lewis number, and you can find it's decrease. The larger the Lewis number, the easier, the smaller the KAC to make the transition occur. Okay. So this is a model. I don't think I have time to go through this. But the Pecnik number here is, this is the Kolmogorov velocity. This is a Taylor length scale. This is a reaction zone because in the spark, it's like a reaction zone. So this is actually a Pecnik number, okay? And all those different data here, all these data, okay, can be collapsed to a single curve when you use the right parameter, okay, except that it's very thin. This transition is 3.6, and this is 4, about 4. So I'm thinking about maybe the spark, okay, because this is the turbulent diffusivity, okay, in small scale. And this is the thermal diffusivity. So in a spark, we think it's a sphere, okay? It's not, it needs like 4 times because the volume of the sphere, the surface, is 4 times of the surface. So it's something like you need much more than 4.4, in order to let the small scale AD attack this kernel, make it break, okay, and make the MAE transition occur, okay, something like that. Yeah, okay. This will take time to I just want to show you some, 2 extreme. So anyway, correlate with the pressure, okay, is like -1/4. So Kolmogorov length scale and the U-prime, which is the same as the Kolmogorov velocity times the Taylor length scale. Okay. So anyway, this fits pretty well, and we have a model. Okay, we have a model for this to explain. Okay. Okay. So I already explained the monotonic MAE transition. So I will spend a little bit time to talk about the turbulent facilitated ignition. That's against the intuition. Turbulence random ignition more difficult. That's everyone accept from the past. Okay, so it's hard to believe in the beginning. How can turbulence facilitate ignition? Yeah. So I'm going to show you. Actually, this is unexpected. Yeah. And the first one, fine. This is a little bit. He just did everything. He didn't measure the CKO lab. He did not measure the MAE, but he controlled the voltage, okay, and their current. So anyway, I don't know what ignition energy they use, but somehow the TFI they can ignite. They cannot ignite the mixture in coalitions, but they can ignite the mixture in turbulence. Okay, so that's the TFI. Okay, and why is that? Okay, so I have originally I don't believe it, and have a debate with Professor Law, and fortunately I spent like 2 years and do experiments to figure out what really happened, and to convince him, and finally, without any argument, he kindly accepted. Yeah, so my pressure is reduced. Yeah, otherwise I was cannot survive in combustion community, I think. Okay, the restrict, what he finds is the Lewis number much greater than 1, okay? But he did not study the gap, spark gap. Spark gap is very important because heat loss is also important, but not crucial. Differential diffusion, because why Lewis number much greater than 1 is necessary, okay? We use the same thing, okay, as CKO, using the same electrode, okay? And the frame end is tungsten W20. So this is 2 millimeter, okay, sharp end, okay, 2 millimeter. This is much thicker. This is very thin, okay. So we look here, okay. So in the coalition there is a very small gap, like a 0.58. You have in coalition there is like almost 250 millijoule. You need for 50% ignitability. But if in turbulence, you only need like 36 millijoule. I will show you in detail, okay? But it's flip if the gap become large. Turbulence random ignition more difficult, okay? And laminar is like a 0.5, very easy to ignite. This is very rich, very rich. 0.1, 3.1, and for the 0.3 millimeter, no TFI for the linkage, for the hydrogen linkage. Yeah, very easy to ignite. Okay, this is 100% at the 0.2 millijoule if the gap is large. Okay, anyway, I think the image will show detail. Yeah. So here is the 0.58. We use post duration time 500 microsecond, and you can see turbulence increase under this TFI occur, and finally they shoot up again. But if the 2 millimeter, we find the monotonic MAE transition. Okay. I think I'm run out of time, so I'm going to be quick. Okay. So the spark gap, you can see, they are so much, okay, very sensitive. Small gap, you have a large, very large. This is a much, this is a rich frame, rich hydrogen frame, okay, 61. And this is 100% igniter. You use 0.2, so MAE is much smaller than the 0.2. But 0.2, we can use small, but it will not square wave. The ignition energy will not accurate. So you can see this image here. So you can see here is the positive curvature here. And the positive curvature, positive stretch, weaken the reaction rate due to the differential diffusion. If Lewis number is much greater than 1, okay? So here, so this is required 250, okay? But the gap to 2 millimeter is dropped to 0.5. Wow. And this 6.5 is so easy to ignite, okay? But for the linkage is like 100%, okay? 100%. And the 50% is only 1 millijoule, okay? This is very small gap, like a 0.58. Okay, so hydrogen is very easy to ignite. Okay, and so in conclusion, the why TFI occur in LE Lewis number much greater than 1 because turbulence may generate negative stretch, and the negative stretch will enhance the reaction rate for Lewis number much greater than 1 mixture. Okay, and this positive will weaken reaction rate. So you need much more energy in order to ignite in coagulation, namely in the turbulence. Okay, so this is for the hydrogen. Okay, so I will conclude my talk very soon on the non-harmonic MAE transition. So this is the TFI. Okay, but the gap. So it's depending on the gap. In summary, I mean, the key point I want to, one of the key points is like turbulent facilitated ignition occurred under 2 restrictions. One is Lewis number much greater than 1. The other is small gap, typically smaller than 1 millimeter. Okay, to have a positive curvature. Okay, in the beginning. Because you need large ignition energy. Yeah. Anyway, so nanosecond is like this is the nanosecond. It's pretty much the same as previous. This is the same. That's the turbulent. That's the high pressure turbulent for successful ignition. Okay, I need to go this fast, and this is the same as before. And that's the nanosecond, okay, enhanced. So nanosecond also has a TFI, okay, but TFI only occur at the post-repetitive frequency for spherical frame, okay. For the jet flow type, the higher the post-repetitive frequency, I think the better ignition probability. But not for the spherical frame, because when you spark and the frame develop, and if you keep it spark in the product, there is no. In the beginning, they have a spark small. They entrain. They have parakinetic torque entrain the fresh mixture. So additional pulse will ignite, generate more radical. And so that can enhance the ignition, okay, in the beginning, in the earlier stage of the kernel development. But later on, when they become the frame, inside the frame is all product, no mixture. So additional pulse is no help. So the pulse will generate. So this is ignition probability will actually decrease. Okay, will decrease. So there are certain range. For this synergistic coherence ignition enhancement. Okay, that's for spherical frame, but the jet flow is different. Okay, jet flow is different. They find it's different. Okay, so this is the picture. Professor Fan, can I talk or just because Tom? Anyway, so he is hasty, so I just quit this. Okay, so the laser, can laser induce spark ignition? Because laser don't have an electrode, okay? So we spark laser here, and they generate the third lobe toward to the laser direction. Why is generate the third lobe? And the laser don't have a TFI. Why is that? Because this toroidal ring has a negative curvature, okay? A negative curvature for the Lewis number much greater than 1 is actually enhance the reaction rate. So make this kernel survive, okay? So it's easy to ignite in coagulation, okay? And in turbulence, they also it's difficult. I mean, because this negative curvature start to fade out, and this lobe is not play a major role, and so it's more difficult to ignite in turbulence. Okay, so the answer could TFI occur in laser-induced spark ignition? Probably not. Yeah, but I only test with N-butane. So I cannot say. And Bradley explained how this third loop occur. You can look his combustion and flame paper to find out this. Pretty much I agree. Yeah. So I already talked the non-monotonic TFI and the monotonic MAE transition. Okay, there are two new phenomena. Okay, and the ignition enhanced. This is Professor Fang want to know, and this is Ji Guang at Princeton University. He used this multi-channel. Okay, and this is Chen Zhen at Beijing University. He used this kind of channel, but this too close. So his energy is really large, and this is better actually. And what I did is we test this. Okay, similar to this one. This is bad. Okay. And this one, and actually this one is much better. Okay, much better, enhanced, much better. So that's in the future. Okay, and we systematically. So my talk is stop here. I thank you, the sponsor, National Science Technology Council, and thank you very much for your listening and attend.
Questions?
Oh. So. Yes.
Thank you.
Professor Zhang.
My question is not about combustion, but sparkling. When you see one of the shock wave be generated, how to control the frequency, the center frequency of the shock wave?
Oh, the shock wave is an order of a few microseconds. Okay. It's hard to control. When you have like a plasma, you have deposited an energy, and in something they generate. Or if you are postulation, some say like a 100 microsecond, but for the first like a 1 or 5 microsecond, they already generate a shock wave, and it's just propagate. It's a supersonic. So it's just of course they take some energy away. Yeah. Something like theoretical, they say 10%, theoretical say 50%, some say 90%. Yeah, but I don't have any way to measure it. Yeah, and the rest they continue to discharge and make the kernel. If the radical pool is sufficient, then it is able to develop to a flame. Yeah, otherwise it's just fade out.
Earlier you used the smallest low of about 0.58 millimeter.
No, 0.3 is the smallest that I use, but the one of the slides show 0.8. Okay. Yeah, 0.8 still has for Lewis number like a 2 greater than 2.2 N-butane. 0.8 still have a TFI. TFI is normally we say turbulent random ignition more difficult. But actually, turbulent can facilitate ignition as long as the gap is small, and you deposit the energy in cohesion that you need because heat loss is large. So you need a large energy, and that makes the barreling torque and the shape is more positive curvature, and positive curvature in Lewis number much greater than 1. Will weaken the reaction rate through differential diffusion. And that's why in turbulence they tear apart, make it less positive curvature. And some negative curvature occur, and that's enhance the reaction rate through the differential diffusion. And so that's why need less energy to ignite. But for the very strong turbulence, is become the MAE transition again, regular MAE transition again.
Thank you.
Yeah, thank you. Yes.
Yeah, really great.
Yes, sir.
Thank you so much for your excellent talk.
Thank you. Thank you.
If we try to kind of extrapolate this from, you mentioned ignition in statistical nature, right? And you
Yes.
try to extrapolate this with this minimum ignition energy where you have a very low probability, to the engines where you're supposed to have very high probability.
Yeah. Engine people want 100%. They don't want 50% or 10%. Yeah, they want every time ignite. Yes.
So what is the probability there? It's like 99.9999 or something like this.
Again, if you want to have 1% or 99%, a lot of experiments has to be done in order to make sure that. Because if you do 10, then 11 maybe, so you have to do at least 100 to make sure you are 99, right? Yeah, or 100. Yeah, and that's not why 50% is like statistics nature is like logistic regression. Get the point much easier to do less wrong. Yeah. So of course I can try 1%. I mean, for very important, that's what I say in a computer server room, store all the data room, and that kind 1% we need. And you have to do thousands to make sure. So even the electrostatics, this kind microjoule, okay, not mini joule, microjoule, you cannot allow to enter. You have to, otherwise you spark it. And the bank information or the, important data information gone. And that's something that we don't want. Yeah. But for the combustion community, it's expensive to do experiments. So 50% is pretty good. Yeah. As long as you have a precise definition and your material, your size, and those information are given, so people can repeat your experiments. That's fine. Yeah, that's fine. I think 50% is reasonable in the academic sense. But you are right. Industry want 100% ignitability. Yeah, no one wants 50%. I have to turn several times to ignite the car. Who wants that car? Yeah.
Other questions?
You want one? You want to? Yeah, try to ask. It's fun to ask.
How did you quantify, like when in the turbulent combustion when it didn't ignite? How did you quantify that?
It's straightforward because when you successful ignition is like you have a kernel, then you develop to the flame, and you consume all the mixture inside the chamber, and if you have a kernel, but it's fed out, that's no successful ignition. That's failure ignition. And if you have a flame and the flame quenched by turbulence, that's also belonging to failure ignition. So it's pretty easy to, by observation. Yeah. Thank you very much. You want to try?
No question.
No? Okay, that's fine.
Okay,
Yeah, that's a 101. Yeah, Taiwan. Yeah, welcome to visit Taiwan. Yeah.
Yeah, let's thank our speaker again.
Okay, thank you.
Yeah. Thank you.